Hello, my voice is audible.
Yes, sir.
Hello.
Yes, sir. It's audible.
Okay, shall we start?
Sir.
Okay. So hereby today I am covering the basic overview of the CST Studio Suite regarding the antenna and RF designing and simulation software. So I am sharing my screen. Are you able to see my screen?
Yes, sir.
Okay. And my name is Darshak Kavad, application engineer Jyoti Electronics and Ahmedabad, Bangalore, Hyderabad. And we are serving the in the platform of the RF and the electronics devices. So basically, Jyoti Electronics is a recognized techno trading company since 35 years. So we are serving with the hardware and software related RF and microwave devices. So we can also provide the design and simulation software as well as the some RF components and the cable assemblies as well. This is our principles. So basically, we provide services from all of this, and we can provide the hardware and software as well. So basically, this is our customer. We already provide the software of CST Studio Suite to ISRO and DRDO, BARC, HAL, BL, and the different IITs and NITs, all colleges all over the India. So basically CST, here we can also deal with the CST Studio Suite. In CST Studio Suite, there is some packages like Spark 3D, Fast 3D, Antenna Megas, Opera, Vastnet. These all are included in the CST. So they can use for the different purposes. For example, Spark 3D. For the Spark 3D, we analyze for the voltage breakdown ratio and the power threshold. We can analyze for the passive component. So after designing, we if you want to see the passive component RF breakdown in which voltage and which power they are breaking down the RF circuit or IM RF component, so we can analyze through Spark 3D. Phase 3D is the same for the like quick analysis of the component RF component. So we can also directly put our design to Phase 3D to CST as well, and we can also analyze quick analysis using to Phase 3D. Antenna Megas is a tool where we have already built in 350 different type of antenna. So no need to go design for the basic scratch. For example, if you want to do design some different type of antenna like horn antenna, patch antenna, and any type of helical antenna, so we directly can put the values of the our RF in the gigahertz and megahertz range. So we can directly use that antenna, and we can export antenna megas to CST, and we can modify that also. For Opera, Opera is using for the 2D and 3D low frequencies analysis. So basically, they are using like designing magnet and electromotors and other electric mechanisms are there. So this is also joined with the CST, and we can also export the result with the Opera to CST as well. Fastness is also tool for the waveguide components analysis. So here for the complex structure of the waveguide, so we can distribute in the small parts and we can analyze the part by. So Fastnet is generally used for the analyzing the whole components using that Fastnet tool in CST. Abacus is some different software that is provided by CST Jyoti Electronics along with the CST Studio Suite. So here is Abacus is used for the mechanical analysis, and we can do material and composite and human tissue analysis like temperature and the strength analysis as well. Also, we provide the MCAD engineering software. So basically, we can say the IVCAD. This is used for generally designing and the measuring the amplifiers and some RF devices are as well. in research and R&D department as well. So in basically here we focus in the CST Studio Suite. So in CST Studio Suite 2025, we can generally cover our overview, and we can also see the patch antenna design and simulation along with the antenna array and the different type of feeding network as well. So CST tool is using to in such a wide range of application like and for that we can also use for in some very big industries like aeromotive, aerospace, communication, defense, and electric and electronics and healthcare, as well as design and simulation fields. So basically CST is providing a different solver with the different application. We will see it further, and for that we can using the CST we can design and simulate the different type of couplers, filters, antennas, PCBs, waveguide, and the different type of analysis like array analysis, SI, single signal integrity, power integrity, and lots of things are that we can analyze with the CST Studio Suite. So here basically the software are there, different software and different solvers are there. So in CST, there is a different solver like a CST Microwave Studio, Cable Studio, PCB Studio, and the Design Studio. There is a different purposes for each solver. We will see right now. For example, CST Microwave Studio. CST Microwave Studio specialized tool to fast and accurate 3D electromagnetic simulation and design software for the high frequency problem. Uh, Along with the good range, because there is a T solver out there, so we can design and simulate the antennas, different type of helix and horn and patch, and we can also go with the waveguides and the filters as well. CST EM Studio, this is a easy tool to analyze the design and static for the low frequency structures. Mostly we can say the actuator breaker and the generator motor like that. Low frequency solver that we can analyze with the RF component. CST Particle Studio is a special tool for the charge particle analysis. So if we have a component like a electrogun and the TWT, and we can say the magnetron and the different type of electron at the charge particle analysis are there. So we can directly use the CST Particle Studio. We can analyze the trajectory of the path or trajectory of the electron and the plasma analysis as well. So CST Particle Studio is used for the special for the charge particle and the electron and some different particles analysis are there during the electromagnetic magnetic field and electromagnetic waves field. So CSTM Physics Studio is using for the thermal and the mechanical analysis for a different temperature. How our component will be resonating. So that will be the shown we can see in the CSTM Physics Studio. So basically thermal analysis are there. CST Design Studio are also there. If there is a complex structure, we can distribute into small parts and we can analyze the one by one. So CST Design Studio is very useful for that complex structure. And CST PCB Studio, here we can analyze the signal integrity, power integrity, EMI, EMC analysis for the PCB structure. So we can't design it, but we can directly analyze the signal integrity and some RF parts analysis like EMI, EMC as well. CST Cable Studio is also used for the analysis of the cables, like cable harnessing and the different type of cables are there. So that is using automobile and many other industry. So we can analyze the signal integrity and the EMI, EMC and power integrity as well. So CST Cable Studio is specially designed for that cable analysis. And basic solver that we can cover is the transient, means T solver. That is used for electrically medium and the large problem. So we can analyze the broadband, and if we can go with the shorter and particularly one frequency like 3.5 gigahertz, so then we go with the frequency domain solver. That is give the more accurate result for particular one frequency. So that is used for the narrow band and the single frequency, and it's also used for the small and the medium size of electric programs and periodic structure as well. And the eigenmole solver, different solver are also there. Eigenmole solver are strongly record resonating, like closed structure like cavity, WTT, and waveguide structure. We can use the eigenmole solver. Integral equation solver are also used for the electrically charged server. Well, generally, we can say the metal structure. An asymptotic solver is generally used for the radar cross-section analysis. They are using SBR method to analyze the uh, component in the space. So for the radar cross-section analysis, we use the asymptotic solver. And film another is a multi-layer solver. Are there like a ground plane patch and the substrate are there and the multi-layer are there. So for that, we generally use the multi-layer solver. So here for the solver analysis, we go further in the CST designing. So many things are there important that we can consider it, like electrically size of the geometry, like antenna or filter or any other component. From that we choose the appropriate solver for the best result in a minimum time. Also, there is a material is important. So because that was we have a material library as well. So you can pick that from that, or we can directly use from the material library, or we can also generate new material as well. We just have to give the this input the property and it will automatically generate that material. There is no problem. Resonant behavior and type of meshing and the boundary condition as well, that is also useful. And acceleration measure are also there. So for the big array antenna, we that's take lots of time, and here we can do the acceleration using. We can reduce the time as well. For the meshing, there is a CST, there is a three type of meshing supported by a different solver. For example, hexahedral meshing are supported by a transition solver, T solver, and the tetrahedral meshing are generally supported by the F solver and the eigenmode solver. And the surface meshing is using in the integral equation solver. For particularly this solver, this meshing are supported and gives the best result. As we discussed previously, according to our requirement, we choose the appropriate solver. Like I want to breadboard antenna. I want to design a breadboard broadband antenna. So we go with the T solver. If I want to narrowband antenna, I will go with the F solver. If I want to analyze the RCS, radar cross section analysis, then I go with the S solver. And CST help tool also there. If during designing you want to check out the what is solver and what is the uses, we can also check directly using help tool. Also, CST have a component library as well, particular with we can directly study and directly import this antenna into your design. So we can use that for our purpose. For example, here I just search the antenna, and different type already built antenna are there. Like we can see the patch antenna, array antenna are there, and we can use it and see it for our learning purposes as well. Also, there is a help tool in every table box. If we do any operation, we can't understand anything like what is the input of this table and what is the input in this dialog box. So we directly can click on the help tool, and there is some guidance are there to for our input what we need to input. Also, there is a concept like in electromagnetic design and simulation software like CST. Generally, we can say that we have an idea. For idea, we are building our design, and we can see we are from the that thing we are okay, since we are designing in the CST like software. After that, we are seeing the results. Results are not good, then we go with the optimization as well. So after that optimization, we are getting our best result. After that, we can go with the final product and the fabrication method are there. So this is for the best tool for the designing before fabrication or before any do another operation done, and see the appropriate result with the good frequency and good high gain range with the antennas and many other components. So this is basically project template when you open the new project in the CST. So they are asking for the which type of you want to design and which type of you go to analysis. Like here I select the microwave and RF optics. So they are basically go for the antennas and the circuits and the RCS analysis as well. There is also like EMI, EMC analysis and the filter analysis and waveguide analysis are there. You can choose appropriate project template according to your requirement. This is basically primary window that is commonly used in the CST. So, one second. So basically, this is a primary window. So we can see the navigation bar. Navigation window. There is a design tools are there. Sorry, design components are there. After designing, they are showing here. Also, they can see the result as well. In the primary window, you can see the design. In the reveal bar, there is a tools we can use it with the designing and simulation. And the parameter list, we can define the different parameters. So you can just see the how the parameter length, width, and the height of the subjectives. And project message are also there. If during the simulation, if the any error are and how much simulation done is, we can show in the project message window as well. So there is some primitives out there already built there. If you in designing, you can use these primitives. You can directly just select any of the primitives and define that length, width, and height. And you can different primitives is already built in like cylindrical spare brakes and the uh, torque and the rotation are there. So you can directly use that. Also, there is some operation are there during designing. If you want to just cut down this of any subject for only per viewing purpose, you also can see the different view option. So there you can see the inside the structure. Also you can see the wire type structures as well. Also, there is a show and hide option out there. If there is a complex structure, above are the outer box are there, and inside something another component are there. So you can generally basically hide the outer surface and use the another inside structure to analyze and designing and modify the structure. So show and hide option are also there. Also, there is a peak operation up there. If you want to do some particular operation for a particular place, there is a peak operation are very useful. For example, we can see the pick the any point or edges or any surface. So you can directly use the pick operation, or you can directly press the shortcut on the keyboard. So after that, double click on the edges. That will automatically pick that one, and also you can see the any surface or edge or any point as well. So after picking the operation, for example, I want to change my coordinate axis from the global coordinate axis. I want to go with the WCS. So I also use the pick operation. For example, in first A figure, you can see my global coordinate x, y, z are there, but I want to simulate with the different one. So the UVW, I just pick the one point, edges point, and deploy the our working coordinate system. So new coordinate system UVW are there. So now they calculate from here from every next operation. For example, I create now the circle. So circle 000 point are there for this coordinate axis UVW. They are not consider XYZ as a global coordinate axis. They consider with this coordinate axis. So that is basically used for the complex designing one by step by step. Also, you can change this working coordinate system to translate and rotate as well. If you already define and if you want to translate this coordinate axis, there is also option are there. Also, there is a Boolean operation are there. So basically, if I have a sprig, for example, we have a sphere and bricks are there. So we can generally add substrate, insert, and dreams are operation, different operation, Boolean operation are there. So we can use it and directly we can use for the designing and purpose of our RF component. So basically here is the curve modeling also option are there. If our design is particularly different that square and the sphere and the different, so we can also use the curve operation. So generally you can define the some points and it will be automatically cover that one, and you can design some random structure. Also after designing that, you can also fill that with some material. For example, in your first picture, you can see the I just designed some random triangular faces and I want to pick with some material. So here I take a piece. You can take any material and fill with any material. So it is also useful. Also, there is a blend and the charm operation are there. If I just generally define my bricks and I want to blend the edges and the charm edges, I can use also blend and charm operation in CST. Also, there is a transform operation are there. If I just design two blocks one by one, and if I want to spacing between that, so I want to transfer first block to another place. So you can directly just select the first one block and transform operation in X, Y, Z and any axis. Also, if I want to rotate the structure, also I use the rotate and the scaling size big and small. I can do also operation that after designing as well. So some operation are there also. Also, there is the shell operation also there. So basically, if you are like using a horn antenna, a horn antenna structure, we can take here example like this one, first one, and we just select the two surfaces that is already connected, and we can operate the shell operation, thick shell inside. So that is their structure will be hollow inside. We can also change the thickness of the outer layer. So that is used for the shell operation as well. We can also use the loft operation as well. If we have two structures, like first one is a cylinder and the second one is a brick, and I want to join them with some another component or the same component, I just use the loft operation. I select the first bricks, and the second one is the cylinder using the pick operation. After that selecting, just operate the loft operation, and automatically they create the in between space materials with the same material. So here you can see the our horn antenna like that, bricks and the cylinder are there automatically filled by width. Also, you can change the angle between that. If you want to change the angle, you can also change that. Also, there is a bending operation out there. If I have a sheet or any solid structure and I want to bend upon some another structure, so I can use the bend operation as well. Also, there is a bending operation is possible in the sheet also. If I have some microstrip like a structure, some thin structure are there, and I want to put in some bending structure like human body or any other thing, so I can use the bending operation as well. After the designing, we can here go with the input section. So we can where we can put the power of our structure. So here where two type of ports are there, district port and waveguide port are there. So in district port, we can generally say lump element using, and 2D port are for the waveguide ports. They both have different purposes, have different meanings, and we can go with both one and as well as a single one as well. For a district port, if you want to design district port, then you have to select one point in positive, one point in negative. Also, you can go with the one point in positive or directly select the negative surface. And after that, select on click on the district port. You can see it look like this one. Single line look like this one. This is for district port. First end is a positive, negative, and negative, positive, anything. That is a district port. In a waveguide port, also you can use the district port as the line. You can directly just select the two lines and two surfaces. You can also use a district port. If you want to go waveguide port, if you want to power all of the component between, so you can generally use the waveguide port. Here you can select any two edges, three lines, three points, and some waveguides are there. So you can directly just select it and click on or define a waveguide port, and it will be look like red one. So it will be give the power to all of the component that is touched by this red plane. Here is a port definition are also there. In the waveguide port, you can directly just define the coordinate axis. If you want to change the size of the waveguide port, you can change. Also, microstrip operation are there, so that will automatically calculate the waveguide port size. If I have a substrate in the above one page and below one the ground plane, I can use the port extension operation are there, so it will automatically calculate the waveguide port appropriate with the good input impedance. If I want to calculate in microchip patch antenna. So after designing, after giving the input, we are doing the simulation, and after simulation we are getting the result. So different type of result we getting are 1D result, 2D result, 3D result are there. So in 1D result we can see the S parameter, VSWR, and some energy and power graph are there. So in 2D result we can see the electric field, magnetic field, and the 3D result we can see the far field pattern of our antenna. We see the different type of result, all standard result, and the we can see here in our navigation tree. For example, here is I can see the we can get power level for the high configuration. Excel ratio also are there, and power level distribution are also there. Also, we can see the 1D result as well as the S parameter based graph and some impedance matching, for example, Smith chart. So we can also analyze this for some particularly impedance. We can say that these impedance are matched or not for 1D result for particularly antenna or for any type of RF component. Also, we can see the electric field and the surface current as well. We can also see the animation of this field. So how can we can see how the electric field be generated through the waveguide port, how electric field and surface current enter through say the port, and it will be distributed in the whole structure. So red part is showing the highest one, blue part is showing the lowest one. So for the from that you can analyze the how electric field be rotating and separating in our structure. Also, as well, electric field, magnetic field, surface current, you can analyze all of three. Also, you can analyze the far field pattern as well, 3D, 2D, and dB graph also as well. You can see the gain as well at the different angle as well. So here is the 3D graph, here is the 2D graph, and this is the dB graph of the far field pattern. Also, you can analyze the gain of the with the phi 0, 0, or you can change the angle if you want to phi and theta want to change angle. And the directivity also of the our antenna or any other component of the RF component in CST. Also, we can see the parameter sweep overview. If our results are not good, for example, I take a microstrip patch antenna and my result is not good, so I want to change the length or of my patch. For example, I have a rectangular patch and I want to change the length of big and small. So I want to use the parameter sweep operation. I can say I used to change my parameter length 4 mm to 7 mm with 0.5 as you can say the 0.5 step size. So that is operation with automatically calculate from 4 to 7, and they give the all the graph you can see here. I have a lots of graph in the for the only one antenna and one S11 parameter. So how I change the length, it automatically change the result. For example, for a 4 millimeter length, that will give the some 2.5 gigahertz, and for the 5, for the 6, 7, 8, 9, 10, for the length are changes, result are changes. So after that parameter sweeping use the operation, you can see here I just take a length and from 21 to 23 here it change the value, and I can see the step also input the step size, and after that we just simulate it. You can see the result will be changed. Here I only take a two operation, 1 and 2. So I can take in many of them. I want 5, 10, 20. From them, you can conclude that it which length, height, or any other parameters you will give the best result. This prototype will give the best result. So parameters is also using for that. Optimizers are also there. Optimizers generally use if our results are not good and if you don't have a better idea, so you can use the directly optimization operation. For optimization, how that's work? For example, I say I want this result. For example, after designing my prototype, it's not giving the S11 parameter good. Generally, below minus 10 dB is the good for the our RF component. So for the especially for the antennas. So I want to go down result. So I just optimize some one parameters. I deploy the length of these points X and Y. Also we can I can say the height and some other parameter also, and I put the in the CST, so that will automatically change minimum and maximum, and we that will give the our appropriate result nearest to I goal. So I give the input, change the X and Y as you can, but I want to result in minus below 10 dB. So that will or that CST automatically change that length, width, and height that I already input, and it will give the best result according to our requirement. Only at one time that will change only one parameter. That will not change directly all the parameters within the optimization. You can change the minimum and maximum value. You can say like minus 10 to minus 20, give me the result between that. I want to result in between that. So optimization are using for that tool also. You can add the goal operation. What is your mind, how result look like, and that is a goal operation it will be considered, and it's give the appropriate trying to match their result. If there is possible, that will give the result. Otherwise it will give the nearest result. So optimizers are using for the tools where we our result are not good and we want to go with the good result of using the optimization operation. Here you can say initial operation are there, below minus 10 dB are not there, red one. But after the optimization, you can see the green one is the after optimization. So that is a good result are there. So we are generally can use that operation into for our better result. Here I take the one microchip antenna example. So basically there is a below one is the ground plane, middle one is substrate, and above one is the patch. You can also see the how the diameter are there, and white color is the substrate, and above one is yellow one is the patch. For that microchip patch antenna I designed in the CST, I got this result. S parameter. So S parameter for the from first graph you can see here. Uh, for around we can say the 4.9 gigahertz. So that means 4.9 gigahertz it's give the minus 40 dB. So that is our return loss. We can see the return loss. That means our antenna is resonating in the 4.9 gigahertz frequency in particular. So S parameter showing like that. And for the voltage standing wave ratio for particularly that frequency, I can see here is around 1. So around 1 is the very good VSWR value for our antennas. So also we can see the 3D graph in which direction our antenna is propagating. So we can here we can say the direction as well as the gain of the antenna. So basic definition in array. After that designing antennas, we can also use the array antenna as well. In array antenna, some single element are there, and we can multiply it with the in height, and the length, and the width project. So we can magnify their gain and the directivity as well. So array antenna is used for the high gain and the with high directivity. CST already built in option are there, so we can directly use for the array antenna. So we can see the, but we can design a large space array antenna. Generally, we can say the element design and the full array design. Here, a small square circle, a small square are there is particularly one antenna. So for the firstly, we design a one antenna. For example, we take a microstrip patch antenna, and then we want to design that multiple antenna. So we directly just select, apply the array antenna, and we can go with the like the 4x4, 8x8 element, and that will automatically create the same antenna in 4x4 row and column are there. So we can use the array antennas. For example, here is some one microstrip patch antenna. And for single element we can see the radiation pattern single element, and after that we use the array antenna task. So click on simulation project, array task. Here I just define the shape. Here I took the octagonal. If I want to rectangular, circle, or like square, so I also select that type of design. And also I here deploy the 8x8 structure. If I want to 16x60, 32x32, that will be the large area that I also can design. Also you can define the spacing between the two elements. You can just define that, and that will be the separate patch during the array function. Okay, and some active and passive element also there. If you want to be if you want to some antennas will be active and some antenna will be passive, so or we can say the off one. So you also can use the active and passive option. Just select the antennas and click on active or set passive components. Also there is some excitation are there, uniform excitation are there, also Taylor excitation are there. So uniform excitation we will give the same power to the all input components. These small one are the some one antenna, small square are one antenna, and all antenna are there. For example, here 8x8 antenna area are there. So every antenna will not give the same power input. Here you can see the middle one is the high gain the high input, and the lower last one is the low input. So power will be changed, reducing and increasing. So accordingly that will the radiation pattern will be shifted, and the gain will be increasing or decreasing. That's why we use a different excitation pattern here. Also unit cell operation are there. So if you want to go with the unit cell boundary condition, you can directly put the unit cell boundary condition in Z minimum and Z maximum for unit cell and the proper mode boundary condition analysis. For also, we can here take a rectangular patch antenna array, for example, unit cell, and how its radiating pattern and the S parameter look like this one. Here I take just example of the 4 by 4 array antenna Taylor excitation. That means I not give the same input, same power input to the all antenna. You can see the different color of that there, but same color operation like blue color, 4 bricks are there. That means that all give the same power, and red color 4 bricks are there. That will all gives the same power, but not all 4 by 4 16 element give the same power. This is a Taylor excitation. If I select the uniform excitation, that means all 16 element I give the same power, and that will be affect our output of the our radiation pattern and the S parameter and the some gain as well, directivity as well. For the 4 by 4 array, array excitation are there. You can see the our radiation pattern with the high gain in the win high output in particularly one direction. So after that, we can go with the uniform excitation. Here you can see the all element are with the same color. That means the all element give the same input power, and you can see the excitation pattern with the same power. You can also see the side lobe in the radiation pattern. So basically they are editing in some particular direction, and we can see the gain and the directivity as well. Same goes for the 12 by 12 array Taylor excitation. Here you can see the our relay excitation with the different input power, and we can see the our input gain and the directivity will increase with the Taylor excitation. And if I select the uniform excitation, that will be gives the small directivity, but that also gives the side lobe as well. Same goes for the 16 by 16 excitation, Taylor and uniform excitation. Array optimizers are also there. Same goes for the data optimizers is for the we use in the CST for the Microstrip edge antenna. Similar like with here one, you can optimize it. You can just change the spacing and the components parameters to get the desired result. Also, there is a feeding network are there. Feeding network is also important. If you use in array antenna, there is a like a series feeding and the parallel feeding are there. So we can here we can see series feeding are there. So all antennas we connect with the one strip line. So that is a one type of series feeding are there, and some there is a waveguide port we use, and another second one is the we can use the coaxial feeding are there. So all antenna connected with the strip line, but that is use the coaxial one. That is use the like strip, like we can see the connector is similar like that one connector, SMA connector like that one. That is particularly second one, series network with the center feed or series network with the microstrip end feed. So here is the third picture is the second and third picture is the center feed. So you can see the back view and the front view of the structure, microstrip structure, array antenna structures. Also, you can see the output of the series antenna and the parallel feed antennas. You can see the radiation pattern change. Same goes same antennas. If you will just change the input type, that will also change the radiation pattern as well as the gain. Here is the electric field and electric field for the series, and the series is for end field and the series network with the center field. They both are series network. Also, we can see the with the parallel in the future. But here is we can see the series field waveguide port are used in both. But in one use this SMA connector like feeding network, and one is the waveguide port connector like they are feeding network. So how our electric field will be generated, you can see here. Here is the input. So the input power and input electric field are generated from here, and the here input is the middle one. So middle they are going to left and right hand side. Also, you can see the parallel field microstrip antenna array as well. Parallel field same goes with the coaxial feeding, or we can see the microstrip line feeding. So S parameter, you can directly compare that S parameter. Which one is the good result you can take as your prototype. Also, we can see the electric field for the theta parallel field networks. You can see the radiation pattern. Also, you can use the parallel field microstrip based antenna area. Here, all antenna are connected with the one strip line, and that is connected with the one port. If you want to go with the different ports, you can directly use the array antenna task and give the all component output as a separate one. Here all antenna are connected and give the same power with the one strip line. So S parameter as we can see, and also we can see the electric field for the antenna and radiation pattern as well. Also we can see the MIMO antenna technology are also there. So basically MIMO is using for the different phase shift. If I want to go with the change with the beam steering and the beam forming operation, so I generally prefer the MIMO antenna. So here is the transmission issue operation are there. So if I get so call with the MIMO antenna, so particularly we can say the what is the concept behind that. Then the for the viral application, MIMO antenna is very useful for the phase shift and the coupling between the two components. So we are generally here is the MIMO antenna, polarization and the spatial additive as well. Also, we can say the parameter justified performance only give the MIMO antenna with diversify gain and the main effective gain in the multiple chain gain. So for antenna, array antenna, 60 for 60 antenna, or we can say the MIMO antenna. How it is different workly. Here we can go. MIMO antenna, massive MIMO, and the beam forming and beam steering operation are there. So here I give the clear view. For a first picture, I just give the one single element microstrip antenna or any antenna. It will look like the its radiation pattern are there, and it will cover lots of things and lots of direction. When I go with the two antennas or two feeding networks are there, any antennas or any ref component, so that will be the combined that input and it will give the output of the some in particular direction with the high gain. So you can also see here our radiation pattern with the four element. The gain will be the high and our output will be good. So also we can change the two radiation pattern with the beam steering. If I want to change the direction in particular, if I want to don't change the my prototype and I want to change the radiation pattern direction, so also you can use the beam steering and beam formula there. So after giving the different input and different phase shift, you will just modify the output of the radiation pattern output and the antennas in the MIMO antenna using the beam forming in different our amplitude and phase shift. So phase antenna also are there. Here you can see the beam forming are there. I just use the all antenna and I just give the different output, different input, and it will give the in particularly theta direction output. So basically, if I didn't give the some amplitude and phase different, that will be theta is equal to zero direction. That will give the propagation. But I want to in right hand side some tilt are there. So because of my input are different, and that will be give the in some particular direction. I receive the some radiation pattern are there. So basically, this is the MIMO antenna, good side of that MIMO antenna application. Also, you can see the S parameter. Here I got the two bands. Below minus 10 dB, I was first is 3.3 and second is the 6.3 gigahertz. That means our antenna is radiating in the two particularly frequency. Also, we can go with the broadband if you can also go with the broadband. Here is we can see the radiation pattern. Red part is showing the radiation pattern in the space. So here we can see the all mostly 90% part are red. So that means our antenna is good enough to radiating in all direction. Like we can see the omnidirectional antennas. So particularly we can see the MIMO antenna that is good for the omnidirection and the all direction propagation and the receiver antenna. Here you can see the radiation pattern of the first and second antenna. Also, there are few LTE MIMO antenna are there. So common ground plane and the common substrate are there, and two different patches are there. Different patches with the good spacing. It's will change automatically the gain in the radiation pattern direction. So we can use the different trial and error method for that one also. Performing the MIMO antenna, S11, S22, 3, 3, 4, 4 are there. So particularly S11 is denoting the return loss for the first antenna of the first input power, and the worst S12 is denoting the coupling between the first antenna and second antenna. So minus below 20 dB for the antennas, it is good coupling for the our antennas in CST. So in particularly S22 and S33 are the return loss for the particularly second and third antenna respectively. So that is below minus 10 dB is considered as good. Also we can see the S parameter for 3 and on 4. performing the MIMO antenna radiation pattern are there. You can see the four antenna with the 90-degree phase difference. So they cover the more angles and more direction. So they will give the vast omnidirection radiation pattern are there. We can generally use with the MIMO antenna. Also, coupling with the MIMO antenna also good. So that's why our waveguide, first and second waveguide and third and fourth waveguide, 180-degree phase different here we can see. So coupling between that, first antenna radiation pattern don't disturb the second one and third one forward. Like that, that is called the coupling. We can show from the S21, S23, S24 like that. That is showing the radiation pattern is not affected by the nearest one or the nearest antennas. So coupling is good in the MIMO antenna because we just change the phase shift of the this component, and we can say the side of the component in MIMO antennas. So everything for the MIMO and array antenna are there. If you have any query, you can ask or you can mail on this email IDs. So we can just provide also some material for that. So for any other queries regarding the antenna array, antenna, MIMO antenna, beam steering, beam forming, and there's some basic design and simulation of the antennas. And you can say the filters, waveguide couplers, and where WTS, and different type of RF component. You can also ask with the same one.
If you have any query or questions regarding the session, you can ask now for the participants. So I think we can wrap up now. And I extend a huge thanks to okay. I think there is one query.
Mhm. You can unmute yourself and ask the query. Or you can directly type here in chat box.
Okay, hello.
Hmm. Yeah, my
Hello,
mail
sir.
ID here now. You can go to email on support@jyotimicrosystems.com.
Oh, yeah. Yeah. Okay. Okay. Yeah. Thank you so much, sir.
Okay, no
I have
problem.
doubts, a few doubts on EMC EMI. So I'll
Okay,
be writing a mail to you.
okay, no problem.
Yes. Thank you so much.
Any other question?
I think we can wrap up here.
Okay,
A huge thanks to Mr. Darshak Kavad and Jyoti Electronics for this masterclass. And
hmm. Okay. Thank you everyone to join us.
thank
I
you.
think we can have a fine. Okay, good.